Hello everyone, we are Group 2, and our topic is Magnetic Encoder and its working principle. I'm going to start our presentation. Okay, so we will first introduce encoder and their basic technology, and then we'll introduce incremental and absolute magnetic encoders and their working principle. Okay, so encoder is a device that can provide moving direction or distance travel by an object for incremental encoder, or the position information for absolute encoder. This difference is because of their working principle, which will be discussed in detail later. And because it can provide position information, it can be used in position control or velocity control, which are largely used in industrial applications, such as motor and machine tool, or it can be used as a digital readout on a manual machine. In terms of the performance of an encoder, there are three terminology that describe it. There are accuracy, repeatability, and resolution. Accuracy, also called position error, is referred to how close the stage moves to the desired location. Repeatability, also called precision, is referred to how often the stage moves to the same location after it repeated several times. So if I control a linear stage to a target position, for example 2 mm, but it is moved to 2.001 mm, this 1 micron error is referred to accuracy. For the repeatability, I control the linear stage to the target position 2 mm several times, and most of the times it moves to 2.001 mm, then we will say that it has a good repeatability. And resolution is defined as the smallest step that can be detected. Here we have several examples to illustrate. For the first figure, the points are far away from the center of the axis, and the distance between each point are also large, so it has low accuracy and low repeatability. For the second figure, the points are far away from the center, but the points are really close, so it has low accuracy but high repeatability. For the third figure, the points are almost at the center and the points are also close, so it has high accuracy and high repeatability. For the last two figures, we have a small dot for the first figure and a large dot for the second. It is clear to see that which one has a better resolution. Typically, the repeatability is the most important factor we may concern when we choose an encoder, because the accuracy can be compensated with a predefined compensation table, so that the object to be controlled is requested to move more than or less than the displacement in ideal condition at every position, to achieve higher accuracy. This compensation table relies on the repeatability of the system. It's because the displacement of the object to be controlled is subtracted by a certain value when commanding to a certain position with compensation. And if the repeatability is low, the position error may still exist. Take figure 1 and 2 as an example. In both figures, if we move the dot to the center, it is clear to see that the range of position error in figure 1 is greater than in figure 2. Okay, so there are several ways to classify an encoder. In terms of encoding method, there are incremental type and absolute type. And in terms of architecture, there are linear and rotary. And several technologies can also be used to encode and decode, such as optical, magnetic, inductive, capacitive, and laser. Two mostly used encoder technologies are optical and magnetic, which will be compared later. For incremental encoder, it only provides the distance traveled by an object and the direction information. So if you want to use it to do the position control, a reference point is needed to be provided. To achieve high resolution, a method called interpolation has to be utilized, which will be discussed in detail later. As for the absolute encoder, there's a unique output for each position, so that it can provide location information It is largely used in most industrial applications, especially in production lines that require the positioning. And it's because if the power suddenly shut down, the machine that equipped with incremental encoder needs time to go back to the reference point. The time is spending results in the cost increasing. That's why the absolute encoder is important. As for the rotary encoder, it's often used as a measuring sensor for rotary motion, so that it can provide information such as angular position and angular velocity. It is also usually used in a lead screw drive system, in which it can transfer rotary motion into linear motion, and by calculation, we can know the position of the velocity of a stage that is driven by the lead screw. However, several error sources may cause the stage in wrong position, such as thermal expansion or power transmission loss in this screw drive system. Therefore, it is often used with another linear encoder for higher accuracy. For the resolution, it is often over in the units of bits. For example, if we have a 13-bit resolution, this means that the resolution is 360 degrees divided by 2 to 13th order, so we have a 0.04 degree resolution. As for the linear encoder, the working principle is same as the rotary encoder. The difference between them is only the architecture. Like I said in previous part, it is usually used with the rotary encoder in lead screw drive system for higher accuracy, or it can be directly used with a linear motor for positioning. And resolution is often given in the units of micron, or sometimes the interpolation factor is given. Interpolation is a method that you divide the pole length into several defined parts. For example, if we have a pole length of 1 mm and an interpolation factor of 4, then we have a 0.25 mm resolution. Here is an example for lead screw drive system with the motor equipped with the rotary encoder, a linear stage driven by the lead screw. Like I said, even if we only use the rotary encoder, the position of the stage can be derived theoretically, but in practice, there are several error sources which cause the actual position of the stage differ from the desired position, so we may install a linear encoder with either the read head or the scale installed on the linear stage to fit back the actual position of the linear stage. But usually, the read head is mounted on the linear stage, with the scale mounted on the frame. As for the optical encoder, it is often used in the application that require high accuracy, repeatability, and resolution, but it has low resistance to the environment, and in most applications, such as machine tool, the metal chip, cutting oil, and dust are generating during the machine process. The environment is therefore very severe. In this condition, optical encoder may occur error or be broken. Moreover, the cost of the optical encoder is high due to its large number of components. It's composed of a LED as a light source, a reticle, and a scale, and a light detecting sensor. Its manufacturing process also increases the cost. As a result, the magnetic encoder becomes an alternative technology with lower number of components. It's only composed of a scale and a sensor. Also, its cost is lower and is more robust in severe environments, but magnetic shielding is needed for magnetic encoder. Its accuracy, repeatability, and resolution may not be as high as the optical encoder, but under the same performance level, the magnetic encoder can replace the optical encoder for lower cost. That's why the magnetic encoder is a promising technology. Okay, so in terms of the sensor used for the magnetic encoder, there are two types of the sensor, which are field strength detection and field angle detection. For the field strength detection sensor, It is usually used in the absolute encoder with non-repeating code, in which the binary codes are paired on the scale, with the north pole as binary 1 and south pole as binary 0. For example, here we have a sensor array that is composed of 2 elements and a 2-bit non-repeating binary called absolute scale. And each element detects the field strength provided by each pole. At this position, 2 elements now detect negative field, so it will output binary 0000 for the first position. And at the second position, it will output binary 01 for the second position. Then it will output 11 for the third position and 10 for the last position. And since the sensor should immediately detect the field strength change from positive to negative or from negative to positive, so a linear field to voltage output is preferred. And in this case, Hall sensor is largely used. And for the field angle detection sensor, it is usually used with incremental scale that has an alternating north pole and south pole as shown in the figure. So this scale will provide a field that is a vector and its x and y components are in the form of sinusoidal, with 2 components orthogonal to each other. So we have a sine term for x field and cosine term in y field. So when an NR element is moving along x direction, the magnetization direction in the sensing layer of the NR element will be changed with the field angle and result in a sinusoidal resistance change. And since the magnetization direction is changed with the field has to be large enough for the sensing layer of the MR element in all directions to be saturated, so that the magnetization can rotate in all directions. In other words, we want the sensing layer to be isotropic, and high MR ratio is also preferred to acquire a large signal. In terms of this application, AMR, GMR, and TMR are used for this application. And for the AMR, we have a maximum electrical resistance when the current direction is parallel with the magnetization direction as shown in the figure, and the resistance is minimum when the current and the magnetization is vertical to each other. And for the GMR and the TMR, we'll have a minimum resistance when the magnetization direction between free layer and pin layer are parallel, like the figure shown here, and have a maximum resistance when they are anti-parallel. And typically, AMR has a 3% MR ratio, and GMR has a 10 to 20% NR ratio, and TMR has a typical 100% MR ratio. And however, the manufacturing process is more complicated in TMR sensor, so the cost should be considered as well. As for the magnetic scale, it is a permanent magnet that has multiple north and south poles for the sensor to read, and the scale used for the incremental encoder and for the absolute encoder is different. In the incremental scale, the scale will be magnetized with alternating north and south poles, so that the field angle is changed along the long axis of the scale. And for the non-repeating called absolute scale, the scale will be magnetized with north poles represent binary 1 and the south poles represent binary 0, like I illustrated in the previous slide. And this scale is typically magnetized through a coil that is designed for certain pole lengths, and the coil will be mounted on a linear stage. In terms of the property, high coercivity and high remnant magnetization are preferred, because we don't want the scale to be easily affected by the external field, and the scale also has to provide a field large enough for the sensor to read, so high remnant magnetization is also needed. And as shown in the figure, this one is the incremental scale, and this one is a coil designed for 1 mm pole length, and this one is the linear stage. So here is the example to illustrate how a scale to be made. So at this position, the current is applied to produce a magnetic field and to magnetize the scale. So in this region, the scale becomes North Pole. Then we move the linear stage with the coil to next position and apply the current in opposite direction, so that in this region the scale becomes South Pole, and we continue the process until all regions on the scale are all magnetized. For the latter part in the incremental encoder, I will use AMR sensor as example. Here we have a MR element and its resistance change depends on the relative angle between the magnetization direction and the current direction, with a maximum value when they are parallel and a minimum value when they are vertical. So at 0 degree and 180 degree, the resistance will have a maximum value, and when they are 90 degree and 270 degree, they will have a minimum value. And so the resistance change will be in the form of sinusoidal, like the picture shown here. Okay, so here we define the coordinate axis on the scale. X is in the measurement direction, and Y is out of scale surface direction, and the distance between the scale and the sensor is called the flying height. And we will assume that in Z direction, the scale has an infinite width, so that the field is uniform in xy plane. And the lambda here in this equation is the length of two poles. And see the picture at the right hand side. We only focus on the field at the same flying height and move the sensor in x direction, so that the field strength the sensor detects is same in all positions, but it experiences different magnetic field direction when it moves along the x direction. Okay, so as the picture shown on the left-hand side is the architecture of the linear encoder, and we will move the sensor along the long axis of the scale. And you can see that in the figure on the right-hand side here, for the MR elements in the sensor, it will experience different field angle when it moves along the scale, and the magnetization direction will change with the external field. And for example, when the sensor is at point A, the magnetic field is upward, and the field rotates clockwise as the sensor moves from point B to point E. And at point E, the field will be downward, and the output signal will be a sinusoidal, like the picture shown here. These two figures are examples for MR elements moving along the scale for one pole pitch, that is 1 mm. And if we only have one MR element, you will find that the output value will correspond to two positions. For example, in the first figure, this output value corresponds to 0.2 mm and 0.8 mm. So we need another signal that is orthogonal to the initial signal, as shown in the second figure. At this time, a certain value of light green curve also corresponds to two positions, but we can compare the value between two signals. In this case, the value of light green curve is larger than the value of the dark green curve at position 0.8 mm, so we can know that it is in the position 0.8 mm. And typically, we will use Wheatstone bridge configuration for the application, because if we only use a MR element, when the temperature rises, this MR element will be easily affected by the temperature, and the output signal may be changed as the temperature changes. So we'll use the Wheatstone bridge configuration to compensate the temperature effect. In this case, all MR elements are all affected by the temperature, so the resistance change resulting from the temperature change will have a little effect on the signal output. And in a fixed pitch AMR sensor, we often use two Wheatstone bridges to provide two sinusoidal signals that are orthogonal to each other. The MR elements in each bridge are 1/4 lambda apart. For example, A1 and A2 is 1/4 lambda apart, and A2 and A3 is 1/4 lambda apart, and so on. So in terms of the magnetic field, they are 90 degrees apart between each other. With this relationship, we can get the voltage output dielectric equation, and the elements in bridge B are 1s lambda apart from the element in bridge A. So in terms of the magnetic field, the element in bridge B has a 45-degree phase shifted to the elements in bridge A. So we have another output like this equation. And because there are two theta term in cosine and sine function, the 45-degree phase shifted between elements in A and B will cause a 90-degree phase shifted in output. And with these two bridge configurations, we can know the sensor moving direction by observing output A leading output B or output B leading output A. Okay, so here we will call bridge A output as phase A signal and bridge B output as phase B signal. With these quadrature signals, we can plot them into a Lissajous circle with x-axis is the phase A signal and y-axis is phase B. And then we do the arctangent to the circle, then we can get an angle to displacement relationship. So that we can know where the sensor is within a pole pitch, and then we count how many poles it passes, then we can know its displacement. Here we have examples to illustrate. In the figure shown here are Lissajous circle and the degree to displacement relationship. And now the rotating vector is pointing in x-axis, so the displacement is 0 mm. Next, the rotating vector rotates to 90 degrees, so we have a 0.25 mm displacement. And when the sensor keeps going, the vector will rotate to 180 degrees. So at this time, we will have a 0.5 mm displacement. And finally, the rotating vector will rotate to 0 degree as the sensor moves through a pole pitch and start the process again. And so, by counting how many circles it rotates, we can know the displacement. And for the direction information, if the sensor is moving forward, then the rotating vector will be in counterclockwise direction, like the animation shown before. And if the sensor is moving backward, then the rotating vector will be in clockwise direction, like the animation shown here. Theoretically, the analog signals can be directly used to decode. However, if we directly output the analog signal from the sensor to the controller and do the arctangent in the controller may not be able to handle such large computation. This problem will result in a limit moving speed of the encoder. So a method called interpolation is used to transfer the analog signal into digital signal and then input to the controller to lower the load of the controller need to handle. In this way, the noise will also have a little impact on the signal during the transmission. Interpolation is a method that you divide a pole length into several defined parts by comparing two analog signals A and B and output two digital signals as new signal A and B to be used. And this two digital signal has one resolution shifted, and as shown in the figure, this encoder has a 0.25 mm resolution, and phase A and phase B digital signal has a resolution shifted. So in the example here, we define the circle into four parts, which are S1, S2, S3, and S4. And we want two digital signals like the figure shown here. So we may define an algorithm that when the rotating vector is in the specific region, and there will be a corresponding digital output. For example, for the dark blue line here, we have output binary 1 in the region S1 and S4, and output binary 0 in the region S2 and S3. So for the algorithm, we can define that when x is larger than 0, we will output binary 1 as for digital signal A. And when x is smaller than 0, the digital signal A will have a binary 0, which is the dark blue line in the figure shown here. And for the light blue line, we have output binary 1 in the region S1 and S2, like the figure shown here, and binary 0 in region S3 and S4. Okay, so for the algorithm, we can define that when y is larger than 0, the digital signal B will output binary 1, and when y is smaller than 0, the output will be binary 0, which is a light blue line in the figure here. But here we have a problem that the resolution is too low, so we can divide the circle into more parts. Okay, so here is an example that the circle is divided into 8 parts, and we now focus on the dark blue line digital output here. Okay, so we have region 1, 4, 5, and 8 as digital output of 1, and the other as 0. So we may write an algorithm for it. Look at the circle. In region 1 and 8, we have x larger than -y as shown in the dark blue region, and x is larger than y as shown in the light blue region. The intersection between these two regions is shown as the green region. And in region 4 and 5, we have x is smaller than -y, and x is larger than y. And whenever the rotating factor is in this region, we will have a digital output of 1 and the other are 0. And for the light blue digital output, we have a region 1, 2, 5, 1, 2, 5, and 6 as digital outputs of 1, and the others as 0. And we do the same thing, but different algorithm. So we can get a new digital output that has a phase shifted of one resolution to the other digital signal. And these two digital signals become new phase A and B signals. So in this example, the resolution is now 0.125 mm. And if we want to get a better resolution for the encoder, we can divide the circle into more parts. And for the direction information, we can check whether the least-reduced circle is in clockwise or counterclockwise direction. For example, we start from 0 degree. If the outputs of A and B change from 1, 1 to 0, 1, then it is in counterclockwise direction. And in other words, the sensor is moving forwards. And if the output of A and B change from 0, 1 to 1, 1, then we can know that it is in clockwise direction, and the sensor is moving backward. Typically, the resolution will be much better than the example in the real application, and the figure shown is a commercial product, high-wind T-type AMR sensor. It is used for 1 mm per pitch, and you can see that the resolution is 1 micron. So in this case, the least-reduced circle is divided into 1,000 parts so that it has 1 micron resolution. Okay, so in terms of the accuracy, we have error source from the scale that result in the position error. That is, the pole pitch is too long or pole pitch is too short. And for example, we have a sensor that is used for 1 mm pole pitch, but it is not used on a 0.99 mm pole pitch scale. So if we move the sensor through a pole, the least-reduced circle will complete a cycle within 0.99 mm, but originally it should complete a cycle within 1 mm. So at this time, we will have a -10 micron position error every time the sensor goes through a pole pitch. And when the scale has a 1.01 mm pole pitch, the least-reduced circle will complete a cycle within 1.01 mm, but it should complete a cycle within 1 mm. So at this time, there will be a 10 micron position error, and overall, in terms of the accuracy, the position error will be in a straight line with a positive or negative slope, and positive slope for the scale that is too long, for the pole pitch of the scale is too long, and negative slope for the pole pitch of the scale is too short. And this too long or too short problem is result from the manufacturing or the thermal expansion, and if the temperature is too high, the scale will be elongated like the picture shown here, and if the temperature is too low, the scale will be shortened and the pole pitch will be too short. So we have to use the encoder under a stable environment, or the temperature compensation is needed. And other than the pole pitch length error, there is another error source from the magnetic field harmonic. In practical, the magnetic field for the incremental scale are not ideal sine or cosine wave. As shown in the figure here, when the sensor is close to the scale, the output signal will be largely distorted. And as the flying height increase, the output signal will be much more sinusoidal wave, like the light blue light. So, and this is because of the existence of the third order harmonics, and the frequency is 3 times the fundamental frequency. That's why it's called the third order harmonics. Also, the field provided by the scale will be much more sinusoidal wave with increasing in flying height. The magnitude of the field strength will also be lower. And to eliminate the harmonics, we will use the principle of the interference. And we know that if two waves are in same frequency and they are in phase, then the amplitude will be larger, and which is constructed interference. But if the two waves are out of phase, then the amplitude will be cancelled out, which is destructive interference. And we will use these principles to eliminate the harmonics. Okay, so to eliminate the third order harmonic, we will add a phase shift between element 3 and element 3, 4 and element 1, 2 to achieve a destructive interference for the third harmonic. As the figure shown here, 1/12 lambda shift is added between element 1, 2 and element 3, 4. And as the figure shown here, we may think it is a constructed interference, but actually the output voltage is the difference between V plus and V minus, not the sum of the V plus and the V minus. So in this case, the third order harmonics can be cancelled out, and in this way, the amplitude of the fundamental frequency will also decay, but the sensor doesn't have to be operated in a large flying height, and if the flying height is too high, the sensor may not be able to operate in saturated region, since the field is not strong enough. Okay, so in terms of the accuracy, the position error will be in the form of sinusoidal wave with the effect of harmonic. So other than these two errors, we also have sensor misalignment error. We have pitch, yaw, and roll angle, and are defined as the rotation about x, y, and z axis in the sensor's coordinate, and is shown in the figure. And since the roll angle will do less impact on the arrow than the pitch and yaw angle, I will not discuss the impact of the roll angle. For the yaw angle, we now only consider the elements in one Weston bridge, and as mentioned before, the distance between each element is 1/4 lambda apart. So they will have a 90-degree phase shift when there is no yaw angle. Now we consider the yaw angle, and the sensor will rotate about the center of itself and move along the long axis of the scale. The distance between each element is still 1/4 lambda, but in terms of the position in the magnetic field, they are 1/4 lambda times the cosine theta apart, and the phase shift will be less than 90 degrees, and this may influence the output. And if the yaw angle is too large, the elements in the sensor may be located at the edge of the scale, like the A1 element and A4 element here, and the magnetic field layer is not uniform and therefore distort the signal. Also, the magnetization in the element may not be able to rotate with the external field when the yaw angle is too large, since the elements now are not parallel to the magnetic field. As for the pitch angle, the phase shift is same as the case in the yaw angle, and the elements are at different flying heights. In the previous slides, we said that the harmonic effect will decrease with the increasing flying height, so the elements will experience different degree of harmonics. As a result, the element's arrangement may be able to eliminate the harmonics when there is no angular error, but the degree of harmonic is different between each element when there is an angular error, so that after the destructive interference for the harmonic, the output may still exist harmonic. For a non-repeating code absolute encoder, the scale will be patterned a non-repeating binary sequence, so that at each position there will be a unique output. And if we want to increase the bit number, we will also need to increase the number of the sensor. For example, if we have a 2-bit encoder, then at each position, it will output a 2-bit binary number. And if we have a 3-bit encoder, then at each position, it will output a 3-bit binary number. Compare these two conditions, we have to detect 2 poles on the magnetic scale at once for the 2-bit encoder, but for the 3-bit encoder, the sensor has to detect 3 poles at once, so that's why we need more sensor for more bits. And because we can only know there is a displacement change when the sensor is moving through a magnetic pole, so the resolution for this type of encoder is a pole pitch, and is limited by the manufacturing process. For a linear encoder, since the length of the scale can be extended infinitely, so the working range is determined by the number of the bits. For example, if I have a 10-bit encoder, then I have 1024 positions, and if the encoder has 11 bits, then it has 2048 positions as the working range, and its resolution is determined by the length of the pole. And for the rotary encoder, the resolution is determined by the number of bits. For example, we have a 10-bit disk, so the disk is divided into 1024 parts. So the resolution now is 360 degrees divided by 1024. And as the figure shown here is the absolute rotary encoder disk. The sensor array has to be located at each track on the disk. In this figure, it's a 10-bit disk, so we need 10 sensors to read for this absolute encoder. And for the linear encoder, as shown on the left-hand side, at this position, the sensor will output 1111 as first position, and output 1110 as second position. And the output only changes whenever the sensor crosses the boundary of the magnetic pole, so the resolution is determined by the pole length. Okay, and to solve the low resolution problem of the non-repeating code absolute encoder, it is often used with another incremental track to increase the resolution. For example here, if we have a 1 mm pole pitch, then for the non-repeating code track, its resolution is 1 mm. And you can see that the output position is like a step function. And for the incremental track, the magnetic pole of the incremental track will match the pole of the absolute track, and provide smaller digits to increase the resolution. And we sum up the output of absolute track and incremental track, then we will get a straight line output with the resolution determined by the interpolation factor. And other than the non-repeating code method, there is another method to achieve absolute encoding, which is nonlinear absolute encoding. The nonlinear absolute encoding utilizes 2 incremental tracks, and if we move the sensor along 2 scales from one end to the other end, the cycles of these are just circles between 2 incremental encoders will differ from one cycle, which means that the lengths of these 2 scales are same, but the pole pitch between these 2 scales are different, like the figure shown here. And for this figure, output A has 16 cycles and output B has 15 cycles. Then the output B is subtracted by the output A. then we can get a signal in the third figure. Finally, we add 360 degrees to the value smaller than 0, then we can get a nonlinear output in which each position has a specific output. In this method, the resolution is determined by the interpolation factor because it uses incremental encoder. And the commercial products are usually offered in 32, 31, and 64, 63 period. This means that we have 32 and 31 period for the Lissajous circles.